Hello everyone, I am Akanksha. Uh, I am PMRFTA for the course Characterization of Polymers, Elastomers and Composites. In the last week, you have covered the topics related to IR spectroscopy, its working, and the types of vibrations using with the help of animations and the Fourier transform. Why do we use Fourier transform in the IR spectroscopy? Then the relation of between the absorbance and transmittance using the Beer-Lambert's law. Then various modes which are present in different molecules. Then ATR equation and Kubelka-Munk theory. Then drift mode and advantages and disadvantages of the IR spectroscopy. Also, we have seen the significance of IR spectroscopy in polymers, and depending upon the concentration of a particular molecule, we can observe the changes in the IR spectrum of the particular organic compound. Then, based on the rubber blades, we studied the grafting in the rubber. Then, essential peaks which are assigned for different elastomers and the region specific peaks. Then, the study of hydrogenation and halogenation, how it happens in the rubber or any polymer. Then, evidence for cyclization and formation of ionomers for basically for conductive polymers. So here's a recap of the IR spectroscopy. So as we know that the in IR spectroscopy is generally it is the analysis of the interaction of a molecule with the IR light. So how, and depending upon how the molecule is behaving in the presence of IR light, so that we observe. And IR spectrum is basically the spectrum in the range of zero point 0.8 micrometer to 1 mm. So we have again classified the IR spectra in three ways, basically IRA, IRB and IRC. So IRA is called near IR because it is near to the visible range. Then there is a mid IR and then there is a far IR. So that is far from the visible range. So that is how we have nomenclatured those. So as we go from near to far IR, the wavelength increases and frequency decreases. So the mid-IR range is particularly from zero point 0.2 to 50 micrometer, and in the wave number, if we convert it, then we will get from 4,000 to 200 centimeter inverse. So this is the basic. This is the region where most of the organic molecules or compounds are shows the IR absorption or transmittance. And in the near IR, certain metallic or conductive polymers can be checked, and in the far IR, so depending upon the different materials, we can observe the IR spectra, but generally for the organic compounds like polymers, we use the mid IR region. So again, we'll come back to the electromagnetic spectrum, how it is happening, the theory behind that. So in the IR region, basically the configuration is changing, and that is how the absorption is happening. So in the IR again, the we can have different range as I have already mentioned, and the frequency and energy depends upon the wavelength of the spectrum, wavelength of the radiation. So basically, for the IR, the material should be having some change in the configuration, or the dipole moment should change. So there are different motions which a molecule can take place. That is translation, rotational, and vibrational. So in the IR, generally vibrational modes are checked, and the vibrational modes can be bending, symmetric stretching, or asymmetric stretching. So now the symmetric stretching again. So if the bonds are stretching in an equal proportion, that means it is symmetric. If the bonds are stretching in unequal proportion, then it is asymmetric. Then bending vibration is again divided into in plane or out of plane. So in plane means the rocking is happening in the same plane, and rocking means like one molecule is going this side and other is again going to the same side. In the scissoring, the molecule is going in the opposite direction, like a scissor. And twisting means one molecule is in another plane, and another is in the opposite. And wagging means both molecules are moving in the same plane. I hope you are able to understand. So rocking means same directions. Sorry, not this one. Sorry. So, and scissoring one is the same opposite direction. So this and this. Then twisting means both are positive. Sorry, one is positive and one is negative. And wagging means both are positive. That means both are in the same direction. Then so this IR absorption is also depending upon certain factors, like the masses of the atoms attached. So depending upon the mass, the IR absorption will vary. Then the strength of the chemical bonds. So double bond, triple bond, and single bond. All of those will be having a specific region of absorption of the IR spectrum. Then hybridization, also depending upon the sp2 or sp3 hybridization, the frequency of absorption will vary. So as I have already told, single bond, double bond, triple bond, and banding vibration, they will be having separate group of frequencies in the IR diagram. Then so we'll talk about the IR diagram again. And the instrumentation for FTIR, that is Fourier transform IR spectroscopy, we use a interferometer, that is Michelson interferometer, and the source is basically goes to the interferometer. It looks like this. So it separates the source in two parts. It splits in 50% goes to the sliding mirror, and the remaining 50 goes to the mixed fixed mirror. And the sliding mirror basically uh, arrange the source light in a certain particular wavelength or wave number, and then it goes to the IR detector. So from the interferometer, the radiation goes to the sample, and from the sample, based upon the transmission absorbance, the detector detects it and plots in the computer. Then there are few important factors which needs to be taken care. like signal to noise ratio. So the signal to noise ratio should be high so that there is less noise in our spectra. And uh, again, the baseline correction should be proper so that the background or the atmospheric other things should not come into picture. And baseline is basically uh, to make the plot even cleaner so that different peaks can be visible to us in a better way. Then resolution. So resolution should be low because uh, the difference should be low so that the we can separate the peaks if they are very close to each other. Then background spectra. So again, if the in the atmospheric, if certain gases or for example, carbon dioxide is always present in the atmosphere, so that should be subtracted from the to check before checking the sample, so that it doesn't interfere with the sample spectrum, so that we can get a better result. So this is the IR diagram. Basically, this region is mostly of the stretching vibration modes, and the second region is based on the bending vibration modes, and the region below 1500 is the fingerprint region. So now, suppose mm, small molecule. So and it has a mass m. So and m1 and m2 suppose, and it is connected with a bond. But let's uh, let's assume the bond is in the form of a spring. So it has a certain spring constant k, and it's if it is stretching, then it is moving in some direction x. So this is the formula for that. So potential energy will be half kx square, and it has a certain amount of zero level energy that is always be there in the molecule. So E naught is equals to half of h nu. And as we increase the bands, the value of n, basically the energy will increase, potential energy will increase, and the value of n should be plus minus 1. So this is the selection rule for a molecule to be IR active. So if the molecule jumps in only one level, the energy will be h
Excuse
nu.
me,
Yes.
ma'am, in previous slide in Jablonski diagram, could you please explain the selection rule once more?
Yes. So suppose your molecule is in the lowest level, and it has to jump with only one, like the difference should be only one. So if it is in the zero level, it will go to one. If it is in the first level, it should go to second, like that. The difference should be only one. So even from 2 to 1 or 1 to 0. So it is either plus or minus of 1. Like the value should be 1. And
Okay, ma'am. Then when it is coming from excited state to ground state, then we can denote it by -1.
yes,
And when it is jumping from ground to excited state, then +1.
yeah, exactly. And sometimes it can
Thank you.
jump to two levels, so that we call as overtone. So in the case of overtone, the peak will be very small, but in the case of a proper, like only one single level jump, the peak will be very intense, like the strong peak will be there. So that is the fundamental of the IR spectra and the selection rule basically. So to summarize, the frequency is related to the force constant and mass. So mu is equals to 1 by 2 pi under root of k by m. So if the molecules are having different mass m1 and m2, we take the reduced mass, that is denoted by mu, and it is m1 m2 divided by under root of m1 plus m2. The molecule may possess only quantized amount, so n should be all integer. So 0, 1, 2, 3, we can take any number, and the molecule absorbs infrared equal to h nu, and so that is the fundamental, and the 2h nu is the overtone. In order to absorb infrared light, the molecule must possess an oscillating dipole. So there should be a dipole moment change in the molecule in order to absorb the IR light. So now,
Excuse me, ma'am.
yes,
Ma'am, could you please re-explain the quantized amount of energy?
okay. So quantized means it is in a so as I told, it is integer, like 0, 1, 2, 3. Right? If you write, if you put n equals to 0 here, there will be a energy at the zeroth level. So that is half h nu. If you put 1 plus, so if you put n equals to 1, then it will be 3 by 2. So in the level 1, energy level 1, the energy will be 3 by 2 h nu. So that is how we can put the value of n, that is quantized, that means it is an integer. So if I go back to this diagram, this is n equals to 0, then it is n equals to 1, 2, 3, like that. So n should be an integer. I hope you
Okay,
understand.
thank you, ma'am.
Yeah. So now let's take an example of the water molecule. So the IR spectra, so as I told, the stretching will be in the higher side and the bending will be in the lower frequency side. Okay, so suppose the this is a symmetric stage, then it will come here in this region, and anti-symmetric stage also will be in the same region, but it is very close to each other. But in case of bending, the stretching, the peak will be lesser, but we can observe the bending mode in the slightly lower frequency. Yes. So depending upon the vibration mode, like stretching or symmetric stretching or anti-symmetric stretching, the spectra will be in the higher frequency region, and in the bending mode, the spectra will be in the lesser frequency region. And in case of a carbon dioxide molecule, we have in plane bending and out of plane bending. So both will come in the lower region, and it will be same only. Like the peak will be same for both. And for symmetric stretching, there will be no peak because the dipole moment is not changing in case of the of CO2. And again the asymmetric stretching will come here in the higher frequency range. Then for moving towards a complex molecule, so it will be difficult, like the IR spectra of these molecules will be little bit more complex and more peaks will be there. So we need to simplify it. So we can see here we have methanol group and methyl group. So methyl group and methylene group. So CH3 is the methyl group and CH2 is the methylene group. And we have set the vibration fixed for CH3. So it will come in this region, like we know the where exactly it will come. And for CH2 also, peaks are very well known for these. So on base of that we can go back to the table which is already there, like in the it is very well established. So with the correlating with that with the wave numbers on in that table, we can check whether which molecule is there. Just a second. Yeah. So upon correlating the wave numbers in the table, we can see which vibration mode is coming for CH3 and CH2 molecules. And there is a fingerprint region from after 1400. So this we need to match with.
Excuse me, ma'am.
Yes.
Ma'am, in the previous slide, it has been mentioned that the CH vibration will come around between 3000 to 29, 300 to 3000 to 2900 regarding, but in CH2 vibration it is so slow, like 1500. Why is it so? Like it also has CH3 also has CH vibration and CH2 also has CH stretching. So
Okay. So depending upon the stretching, so as I've told, there is a for CH3 we have a umbrella stretch. So all three molecules of hydrogen will stretch in a fashion of like as we open the umbrella, it will move like that. So so that mode of vibration will be distinct with the CH2 vibration, right? So that's why the peaks will be different for those all. But still these are called these all are CH stretching only. Okay, but the modes are different. So that's why we get different peaks for different groups basically. I hope you understood.
a little bit, ma'am.
Yeah, so I hope you have seen that animation video of different molecules, and there are a lot of examples related to this. So you can go back to that one and you can again try to understand how why the peaks are different for CS3 and CS2. So basically, the stretching modes are different. So that's why the peaks are different. That is the only reason I can say. So you can again go back, and so with the help of animation, you will able to understand better. So I will recommend to check the lecture. I think the first lecture of this week, week fifth. So you can check that.
Okay, ma'am. Okay.
I've told about the fingerprint region. So now we are going to the Fourier transform. Why we are using Fourier transform? So basically, it is used to transform the function from time domain to the frequency domain, so that we can easily resolve the frequencies and so that we can get a better resolution of the of our spectra. Again, a little bit about the Beer's law. So Beer's law states that the absorbance is proportional to the concentration of the material and also the path length. So this in this case, the absorption and transmission relation is given, and absorbance is equals to minus of log 10 of transmission. So it is basically opposite, and if we plot the log of transmittance, we get absorbance, and vice versa. So there are three controlling factors: the molar absorptivity of the solution, then the path length, which is the distance traveled by the light in the sample cell, and the concentration of the solution. So all these three factors are affecting uh, the signal which we are getting. So there are different modes of FTIR basically. So depending upon our sample, we can use different modes. So first one is the transmission mode. In transmission mode, what happens is we place the uh, film or any glass slide or anything which is coated on with the sample in it, and the IR radiation will pass through it, and there is a detector that detects the absorbance or transmittance from the sample. And in the case of reflectance, suppose the material is uh, not uh, not able to transmit the light or IR radiation. In that case, we take the reflectance from the surface, and then it the reflected light goes to the detector, and again the signal is processed. And suppose if there are small particles, then in the reflectance mode, the problem can be that the uh, rays will be scattered all over the place. So the detector will not able to detect the complete radiation coming from the sample, and in that case we will not get any signal, or the signal will be very less and noise will be high. So signal to noise ratio will be very low. So in such cases, we use drift, that is diffuse reflectance IR spectroscopy by Fourier transform. So in this case, we use a semi-spherical surface kind of thing. So the IR source goes to this surface and goes back to the sample, and the sample scatters the light in all the directions, like majorly in this direction. And uh, it these are so this is a converging lens, so it converges the light to the detector, and then the detector detects what is the absorbance or transmittance from the sample. So in that in this manner we can check the scattering or from different particles, or if the surface is very rough, in that case we this is very useful. And then we have attenuated total reflectance, ATR. So this is basically used for checking the surface properties. So we have a crystal here, it can be diamond or ZnSe or gallium crystal, and the IR radiation is passed in such a way that the total internal reflection will occur. So angle should be like that, that the total internal reflection occurs in the in between this crystal. And the sample is placed very close to the crystal here. So the sample is placed very close to the this crystal, ZnHe crystal, and the IR radiation is falling in such a way that multiple times it is striking the sample and the absorption is happening. And finally, we check the radiation at the outer side, or at the last end of the crystal, and then the detector detects how much light is absorbed to the sample. So this is a very good mode for checking the surface property of any material. And also, so ATR equation, this shows that how much depth of penetration will happen once the IR is getting striked on the sample. So the depth of penetration is can be determined from this formula. Here lambda is a variable, so we can vary the uh, frequency or wave number of the of our spectra, and so that we know in uh, which wavelength or at which wave number we are getting the maximum depth, and depending upon that we can analyze the spectra. And it also depends upon the reflective index of the sample and the support. So this NSP is the reflective index of the sample, and P for the support. And the theta is the angle of incidence, and I sorry, this is lambda. Lambda is the wavelength. So, for example, if we are using ZnSe, we know the this refractive index of the support, and a polymer sample will be having a specific refractive index. In that case, we can get a depth up to 2 mm at a wave number of 1000 centimeter inverse. So in such a way we can, if we want to check the how much depth it is going inside the sample, so that in that case we can check. So
Yeah. Excuse me, ma'am.
yes.
Ma'am, the depth is not clear and the refractive index of support. What's the support mean here?
Yeah, support is the crystal, ZnSe crystal. So here we have a sample. The sample will be having some refractive index, and this crystal. So the crystal is also having some refractive index. So I think you have read about the refraction phenomena.
Yes,
You are aware of that,
yes,
right?
ma'am. In physics.
Yeah. So refraction is it depends on the refractive index of a material, right? So uh, so depending upon that we can check how much uh, depth of penetration is happening. Depth of penetration means, so we are keeping the sample very close to the crystal, and we are So, assuming that only the surface is getting exposed to the IR radiation, but there is a little bit amount of radiation, it is going in depth of the sample. It is not only in the surface, like the depth will be very less, but it will be there. The depth should not be equal to 0. Okay, there will be a little bit of depth. So if I draw it, I'll try to
Yes, ma'am. Clear, ma'am.
clear. Okay, so that is the depth of penetration. We can determine from this equation. So the advantages of the ATR systems are it is easy to clean. So the crystal can be just easily wiped with a solvent of the sample, which is the appropriate solvent basically. And there is no sample preparation. We just need to keep the sample on top of the crystal and check the ATR. Then it needs to be simply placed on the sample, so that is not a difficult thing. And the path length is consistent, so we know that the crystal is having a particular dimension, so the path length will be very uniform all over. And the path of energy into the sample is constant for each sample. So that energy, so basically the path is constant so that we can get the proper absorption for a particular sample. And so it is not suitable for corrosive liquids because the crystal can react with that. And soft powders can be hard for this, so that so normal uh, normal modes can be used for that in case of powders. Then we have Kubelka monk theory. So this theory tells about the relation between absorption and reflectance. So this uh, it shows, so this R is the reflectance and A is the absorbance. So it gives the relation between reflectance and absorbance. And if we have a graph of reflectance, then we can convert it to absorption spectra, and we can try to make a calibration curve if we want to uh, check the concentration of a material. So for example here, so we can make a calibration curve. So this is a calibration curve. Suppose 3 points we have taken, 3 or 4 points, and uh, depending upon the absorbance, the concentration will be fixed. So, and if we want to check an unknown sample, so suppose it comes in between here, so we can depending upon the absorbance how much it is coming, we can correlate it with the concentration. So in so that's how we can determine the concentration in a unknown sample. So this is very useful in such cases. So only with the help of reflectance we can correlate it with the absorbance and the concentration can be determined. And also so these, if the peaks are very near to each other, then or if it is not so much dissolved, in that case we need to deconvolute those peaks if they are overlapped basically. So this deconvolution is a helpful process and it is done mathematically. in any of the softwares like Origin or anything. And then we do the curve fitting also. So it is a process of constructing curve on the mathematical function. So that can be easy to determine how the how suppose there are, so these are some of the points I'm getting, but I don't know if it is a linear curve or polynomial. So I try to fit it in the with the help of a mathematical function. So this will come as linear. So now I know that the relation between the absorbance and concentration is linear. So that is how with for different data points we can try to connect it with a function, and that's how we get to know about the relation between the two variables. So now drift. So drift is depending upon the Kubelka-Monk function. So and it converts the signal to into absorbance. So as I have already told you, this theory, it connects the reflectance and absorbance. So in this case, the sample preparation can be done in three ways. So we can fill the there is a micro cup. So I'll go back to that diagram. Yeah. So in the here we place a micro cup and the sample is placed in so suppose the sample is in a powder form, so it is mixed with the KBR. So KBR is uh, it does not absorb IR, so that's why we use KBR, and we mix the powder in KBR and keep it here in the micro cup, and then we uh, incident the IR light, IR radiation on that, and we check the scattering or diffused reflectance from the sample. And the second way is to scratch the sample surface with a piece of a abrasive or silicon carbide paper, and then check the particles on the paper which are adhered to the paper. Then the third way is that we can drop if it is a liquid, then we can drop the solution on the substrate or KBR or any other like substrate which is IR transmittance, and so if colloidals or powders are dissolved in a solvent, in that case we can dropcast it on the substrate or KBR, and we will wait for the solvent to evaporate, and then the remaining particles of the on the substrate can be uh, checked in the drift arrangement. So there are certain advantages of IR spectroscopy. So it is a universal technique. So that means that we can use solid samples, liquid samples, gases, semi-solids, powders, and other polymers can be checked. Then IR spectra are information rich, so we can so depending upon the peak position, its intensities, and width and shape, whether it is broad or small, or peak is very weak or very strong, depending upon that we can easily tell that what molecule can be present or what functional group can be present in the material. Then it is a fast and easy technique, so it doesn't take much time, and sample preparation also doesn't take much time. And it is very sensitive. Even if in the microgram or nanogram quantities we can detect. So in that cases, the this IR spectroscopy, that's why it is very helpful. There are some disadvantages like homonuclear compounds that cannot, which does not show any change in the dipole moment that does not absorb IR, so we cannot detect those. Then aqueous solutions are difficult to analyze because the water absorbance will be there, so it sometimes interfere with the actual peaks of the material, and we cannot get the signal properly, so that needs to be taken care in some ways. Then some compounds give broad bands, so that interferes with other compounds, so that is an issue. Then complex mixtures are difficult to separate because in single molecule itself there are a lot of peaks. So if it is a very complex mixture, then it is very difficult to separate those. Then black compounds are cannot absorb IR, so that will give 0% transmittance, and so it absorbs IR completely. Sorry, and that's why it gives zero transmittance. So those are difficult to analyze, and uh, similar property of molecule cannot be, so if a material having similar properties, then it is very difficult to uh, differentiate those, so because it does not give the information about the molecular size, so those kind of molecules are difficult to uh, differentiate. So in such cases, this is not a good way to check that. Then there are certain state of the art uh, modification of the FTIR. So this is a setup which is having a three neck beaker, and one side we have the FTIR detector. So this is connected with a optical fiber, and so as you can see here, so one side gives the incident radiation, and the other one detects the radiation which is uh, reflected from the surface. So for the liquid samples, this is a good technique to check the FTIR for this kind of samples. So now we have so these are the commonly found stretching, vibration, or chemical groups which are there. So depending upon the material, so we have a fixed number of absorption bands. So suppose we have natural rubber, so in that case we will get these four kind of bands that is fixed. So if it is mixed with so for example some uh, other compound is mixed with the natural rubber, so in those cases we can check that these four groups are present, so that means natural rubber is all there, but there are certain other peaks are there, so we can check what are those. So depending upon that we can uh, conclude that this material is having these things. So natural rubber shows peaks, so these are some of the peaks, so C11C, then CH3, C11C, and other additional products of isoprene. So these are some of the assignments which needs to be assigned in a particular IR spectrum. So again for butyl rubber, again we have four set of peaks. Then for SBR, again there are peaks for benzene and butadiene part. So these are some of the standard peaks which has to be there in a material. If it is styrene butadiene rubber, these peaks should be there. Then EPDM, again these are the peaks which has to be there. So and similarly for other different types of polymers, these are the set of peaks which are standard. So this you will find in if you do the FTIR of a particular element, you will get this kind of peaks. So this you do not need to remember, but still some peaks which are very standard that can be remembered, because those will be repetitive in all. For example, this carbon double bond. So in the 1600 region it will be there. So those some of the peaks should be remembered, and not all has to be remembered. And again, for silicon rubber we have these four peaks. So at 1019 we have silicon oxide, then 2 1 2 3 4 silicon with methyl group, then 800 silicon with carbon, then 680 sorry 865 this CH2 So these are the peaks which are assigned to the silicon rubber. So in a standard silicon rubber, it has to be there, and there can be other impurities or other things also. So in that cases, other peaks can also be present. Then for EPDM rubber, so we have dyne stretchings. So dyne groups are there, and then we have norborine. There is a base element monomer, so that needs to be there. So we need to check uh, the basic unit of that, and depending upon that the stretching and bending peaks are assigned. And this is uh, the for checking the chemical modification of rubber. So suppose this is the molecule, and if there are the modification such a way that the structure becomes trans or cis kind of thing, or other kind of configuration if takes, so the shift will be there. So we can know that the shift is there depending upon the cross-linking support, for example, or you have done other chemical modification or other additives you have added. So in that cases you will be able to observe the changes in the peaks. So peaks will be shift. If the conjugation is there, the peak will shift to higher frequencies. If some other substitution is there, or broadening of peak can happen, or shifting of peak uh, can happen. So those kind of changes you will be able to see very well in the FTIR spectrum, because it is very sophisticated. So even a small change can be observed. So here so different kind of peak will be there in the different arrangement. So for example, wagging can be seen in this region. And so similarly, if for a styrene we will get a peak at 700 centimeter, and 909 peak will be corresponding to the butadiene. And this will, for that we can monitor the ratio of the styrene to butadiene, and in that styrene butadiene rubber we can calculate the ratio how much it is coming, basis on the basis of different modifications of the rubber. So now so what is grafting in the case of rubber blends? So what does it mean? That we are using diabetyl maleate to graph the polyethylene and EPDM. And so this can also be observed from the FTIR. So you can see that the peaks are getting diminished, or some peaks are getting increased. So and new peaks are appearing. So those kind of changes you can see in the spectra, and you can check whether what is happening in the with the help of your the modification which you are doing, what is happening in the material exactly. So this is a PVC FTIR. So in this, so we have chlorine, then CH3, and why C double bond O is coming? It is because of the oxidation. So if it is kept in the air for long time, then the peak will be strong. So in those cases, we need to observe what kind of changes are happening in the polymer or in our material upon exposing it with air, or upon keeping it for long time in the atmosphere. So those kind of observations can also be done using the FTI. And so again, milling, and it can be used for different applications, adhesives and other things, like if a degradation is happening in the material, that chemical changes can also be observed in the studied in the IR spectroscopy. Then reverse engineering can be done. So this to analyze which material is present in a unknown sample. That in that case we can use the IR spectroscopy with the thermogravimetric analysis and other analysis like HPLC or other. So this is a very helpful technique in that case. Then hydrogenation. So what is hydrogenation? If we are keeping the sample in acids, or we are trying to increase the degree of hydrogenation, in those cases we can observe certain peaks are getting diminished. So this 970 peaks is getting diminished upon hydrogenation, and new peak is coming. So this kind of uh, so this peak at 723 will appear, and its intensity will increase with the degree of hydrogenation. So in those cases we need to observe this kind of peaks. So there are different examples for different material. We can uh, check the degree of hydrogenation using this formula. And so this is one of the process. Then we have halogenation. So in this case, if we are substituting halogen like chlorine or bromine or something, then the degree of halogenation can also be determined using the FTIR. So many examples are there. PVC are there, and VR, butadiene rubber. So various polymers can be checked, and depending upon the our requirement, we can choose the particular uh, percentage of hydrogenation or halogenation. So these are some of the characteristic peaks which are assigned to the for different modifications. So for example, hydrogenation, these peaks needs to be checked. These are the characteristic peaks basically. So for chlorination, these peaks are at these positions needs to be checked. For bromination again, these, then cyclization, then hydrosilylation. So many things are there, like oxidation, sulfonation, ionomer, a lot of things lot of modifications can be achieved. So cyclation means the rubber or elastomer is kept in a concentrated H2SO4 solution. So it is taking the hydrogen ion and making a ring kind of thing. So this is a formation of a cyclic benzene ring. So these kind of changes can also be seen in the FTIR, and it will be more prominent in this region. Uh, and yeah, so there are a lot of examples for this also. So suppose this polybutadiene, these peaks will be there, and some of the peaks can disappear and new peaks can emerge at 820 and 3040. So those kind of changes can be observed. Then the peak at 750, 740 can falls off, and the peaks at 820 will appear intensely, and so that will give the degree of cyclization, and if the intensity is increasing, the degree of cyclization is increasing. So these are some of the characteristic peaks which needs to be checked while performing a certain type of modification. Then ionomers. So ionomers are these are the polymers which are having conductive group in it. So to make the polymer conductive, we use certain ionomers to so that the presence of ion can make the polymer conductive. So this is getting so here this is getting modified in such a way that it is forming a Na plus ion here. So this is basically helpful to make the material more conductive. This is also can be checked in the IR spectra. So here in the far IR, we have to check for these kind of ionomers, because sodium is absorbs in the 220 centimeter range, and whereas cesium it is the cation which gets absorbed in 100 centimeter inverse. So for that cases, we need to check far IR spectra. So depending upon the application again, we need to check the range of the IR, what we need to check. So now let's come to some of the questions, assignment questions, which are used in the previous lectures. So which one of the following statement is true? Homonuclear compounds don't absorb IR radiation. Twisting and wagging modes are out of plane vibrations. Black, dark black compounds often show 0% transmittance, or all of the above. Can anyone tell me what is the answer for this?
All of the above, ma'am.
All of the above.
Yeah, exactly. So, as I told, homonuclear compounds means there is no change in the dipole moment, so it will not show any IR absorption. Then twisting and wagging, as I've already told, these are out of plane vibration. Twisting means in the opposite direction, and wagging means in the same direction. Then dark black compounds, it radiates light, but it does not show any transmittance. It absorbs the whole light, whole IR radiation, so it does not show any transmittance. So all of the above are correct. Then Kubelka-Monk function is used in IR spectroscopy drift mode to convert signal into absorbance, wave number, frequency, wavelength. Which one should be correct?
A.
Yeah. So exactly. So the function, the signal from reflectance is converted into absorbance. So answer A is correct. Then which one of the following chemical is used to make palette in FTR spectroscopy? So I think someone can tell me the answer.
KBR.
KBR, exactly. It does not absorb any iron, so that's why we use KBR. Then for the to calculate the lambda max for the following element, can anyone tell me how to calculate the lambda max? This was from the previous week. The absorption.
First of all, ma'am, we will have to take the base value
Yes.
and then the substituent attached with it at alpha or beta positions and the dynes as well.
Yeah, exactly. So for this case, this kind of a structure, the base value should be. So I'm coming to the answer. So for these kind of structure, the base value should be 215 nanometer. Then alpha alkyl groups are present. So there are 10. So for 1 into 10, so sorry, one alpha group is there. So and the residue will be 10 nanometers. So 1 into 10 is 10. Then beta alkyl groups, so two are there, and the chain should be 12. So 2 into 12, 24. So that is how we calculate, and it is 249. So here 249 is the correct term. Then match the following for IR spectroscopy: transmission, drift, ATR reflectance. Can anyone try to correlate it with this?
Ma'am, transmittance would be for thin film
Yes, exactly. So that
and drift for Kubelik-Monk theory, ATR for ZNNE, and reflectance for shiny sample.
yes, correct. So I'll explain again. So for transmission, we generally require thin film so that all the radiation gets transmitted from the sample. And for drift, as I have told that Kubilka-Monk theory is useful. So from the reflectance, we can convert the reflectance into absorbance, and we can correlate the two properties. Then ATR, in the ATR we use ZNS crystal, so it is the correct relation. Then reflectance is generally used for shiny sample because and that gives very high reflectance. So that is a useful property in such a case. So transmission D1D, so 1D, then drift, uh, sorry, 1C, 1C and second D. So C is the correct answer. So anyone else have any questions? We are done for this session as of now. You can ask me doubts if you are having any doubts.
Could you please take the first question?
Yes, yes, sir.
Which one of the following statement is or are true? Uh, Homonuclear compounds don't absorb IR radiation.
Yes,
How can you explain in terms of CO2 and H2O.
So homonuclear means both are having uh, similar molecules, like uh,
H2, O2, Cl2.
no, like similar, like ClCl, or like that. So if we have HCl, that means H is having some dipole and Cl is having like H is positive, Cl is negative. So there is a change in the dipole moment. If both are negative, then in that case there is no change. So if two molecules, if a molecule has two similar atoms, in that case absorption will not happen because the dipole moment is not changing. So that's why, like, that is the basically it, it does not absorb any IR radiation. That is what I want to say. Mm. And also in case of CO2, as I've mentioned here. So suppose, this is carbon and this is two oxygens are there. So if the stretching is equal in both the sides, then both are, there is no change in the dipole actually. Both are having similar charge. So in that case, there is no vibration. So there is no absorption basically. So I can so these are homonuclear because there is the dipole moment is not changing because both are stretching in a equal amount. While in case of asymmetric, uh,
It's a CO2 molecule, no?
sorry, yes, this is CO2.
The CO2 molecule.
Yeah.
So CO2 molecule is a homogeneous molecule.
So we cannot say like that, but uh, homonuclear means similar kind of molecule, like both ClCl or like that H2, hydrogen, like that.
Okay. So,
Okay. Any other questions?
from my side, no question actually.
Yeah, yeah,
Actually, to be fair, I'm facing little bit difficulties in this area because I'm not a
yeah.
chemistry
It
person. Basically,
happens. Yeah,
that way. So this kind of some basic understanding is required. Okay, anyway, we'll pick it up.
yeah. You can ask basic questions also. That is not an issue. Like I'll try to answer. I, I also don't know
And
everything, but I'll
other
try
thing,
to answer.
yeah, wave number and all these things that base. So he mugging up all these things is very difficult, no?
Yeah, exactly. So
This,
you don't need to remember the this table. We always try to
yeah.
refer the table. These are very standard, like characteristic positions for this particular stretching. So these you will be easily able to find online,
Uh,
and so in in my research also, if I want to check the characteristic piece, I always refer to the standard books and standard
Yeah.
tables. So this does not needs to remember, but we should know like very basic things like stretching will come at the higher frequency and bending will come at lower
Yeah.
frequency, like that.
That is the that basic
Yeah,
fundamentals.
yeah. So those fundamentals just needs to be remembered, not everything.
Could you please take the last question?
Yeah, yeah.
That the structure of last question.
This one.
Just before that, one structure you showed.
Yeah, this one.
Yeah. Calculate the wavelength maximum for the following compound. Now the same that the same thing after 249 you told. Could you please explain it once? That
Yeah,
how
actually,
you
this
reach?
I mentioned in the last session which I took. So this is an
Yeah, yeah,
old
yeah.
question basically. I'll try to open that file. Yeah, here. So there are some base values assigned to a particular group.
Okay.
Yeah, here,
And in that,
here lot of
how you
yeah.
uh,
So here lot of things are there. Like for example, if a ketone is present at alpha or beta position in a cyclic molecule or in aldehydes or carboxylic acids, so those cases we need to take these kind of base values. Then if alkyl substituent is there in a ring or alpha position, then we need to add this 10 nanometers. If it is in a beta
yeah,
position,
same,
then
same thing.
12 nanometers. So these are all standard values we need
My
to.
question is how you identified that actually base, okay, that base value we can, okay, by looking that that structure,
Yeah, look
sometimes you
at
may be
like that only we need to
okay, the
check
base.
because
Ah, here in alkyl group for ring residue,
or
how you identify it? One is 10 and beta alkyl group or
so
ring
these are
residue 2 into
basically
12.
positions of the group which are at, so alpha and beta are the position. I hope
Uh-huh.
you have read it in the like very basic chemistry classes. So
Yeah,
alpha and
oh,
beta are the positions at which the uh, group is attached. So suppose we have a benzene ring and we have
oh.
alpha beta, like in the benzene we have para and other thing. In the normal chain we have alpha and beta positions. So for that, in that cases we use this kind of nomenclature: alpha alkyl group and beta alkyl groups or ring residue.
Achha, by looking that structure itself, you can understand
Yeah,
that.
yeah.
But now by in that structure, could you please just explain what are all these alkyl group where it is attached? By just for
Yeah,
sake
yeah.
of understanding,
So,
because that basic idea I don't have.
yeah, yeah, it's okay. So, the base value for this is 215. So, I'll go back to here. So it's a six-membered cyclic alpha beta unsaturated ketone. So ketone is there. Here the ketone group is there, and
Okay.
it is like if you complete the benzene ring, it will give a cyclic structure. Okay.
Okay.
So
Okay.
that is the base value for this structure 215 nanometers.
Okay.
Okay,
Right.
then there are three groups present. Okay.
Okay. Okay.
Uh, so imagine this is a ring and three groups
Ah.
are there. So one
Okay.
is
Three.
the
Three.
alpha
Yeah. Okay.
group. So 1 into
Ah.
10 and 2 are
Ah.
beta. So 2 into 12. Okay.
Now, among these three, how you identify that which one
Yeah.
is alpha, which one is
So
beta?
this
You just
middle one is should be alpha and this two will be beta. I
ah.
and so this one and two, so two beta and alpha is
Ah.
one. So one into 10 and
Okay.
two into 12. So that is how we calculate.
Okay. Right. 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 I agree.
Okay.
So in all the cases, it is like that only. This
Yeah, yeah.
alpha will be in the.
Yes,
Uh,
exactly.
okay.
And
Okay. Okay. Then suppose that some two attachments are there. Only two attachments are there.
yeah. So
Assume
suppose only
that way.
this and this will there. So one alpha and
Ah,
one beta will be there. So in that case, 1 into 10 and 1 into 12. So the
okay.
number will be this.
Only one attachment is there means it will be treated as alpha only.
Yes. So if it is in the middle, then
Ah,
it is alpha, and the other two position, then beta.
oh, beta. Okay, okay. That is the identification.
Yes.
Okay. Okay. Okay.
Any other questions?
Now, for me, it is okay. And some more questions are there. I will. I will next time. I
Okay,
will
sure.
collect it and. Thank
Sure,
you.
sure.
Thank you.
Anyone else have any questions? Okay, if not, then we can stop the session here. Okay.
Okay. Right.
See you in
Thank
the
you.
next